Okay, so once again, we were talking about different kinds of benchmarks. We talked about different organizations on the previous slide, and SPEC, I said, was the most important one. Or most, well, I shouldn't say important, but is the one that is used by many, many different applications as compared to the other ones which have some limited set of applications. So SPEC has many benchmarks starting from graphics rendering to CPUs to Java and so on and so forth. And really only when you need one of them you will go and read about them. I don't want you to go ahead and read exactly what it is because that is not really important. It is important to know that this thing exists. So if you are looking for a benchmark, obviously you should look for specs. SPEC benchmarks and others which you can easily find. So the CPU benchmark, for example, in SPEC, which is 2006. Here it consists of many programs. Actually, most of the SPEC benchmarks are like that. Is that a member says, okay, here is a program that we run very often. Let's see how other systems will perform on this. So this one, CPU benchmark, consists of many programs contributed by the members. And if you go to SPEC website today, you will find they still have open for SPEC whatever number CPU benchmarks. Next one, you can contribute a program that you have, that you feel is important. Obviously, it will not be accepted unless a lot of other people feel the same way. So this is a big organization, and then people vote upon what is an important application. But anybody, members, open source or academics, can contribute their program. Ported to various platforms to remove dependencies on I/O and operating systems. So if you have a program running on Windows, obviously if you take it there, they can't just take it Windows version. They will have to make sure that it runs on Linux, it runs on Mac, it runs on everything. So the level at which the benchmark has to be specified, or the application has to be specified, is much higher level. Like it might be a C program, which can be compiled for any of these systems. Compilation and execution is automated, and so nobody can play with that part as much as possible. So they will give a program, and then they will say, well, here is the command line for C, and tester supplies a configuration file with location of C, compiler, compilation flag, etc. And then what it measures is speed. And the speed is defined as the execution time on the system normalized by a well-known system. So in the days when I was actually active in SPEC, that is 20 years ago, by the way, 1984, 30 years ago, my God, time goes fast. So in those days, the standard system was VAX. I don't know whether any of you have heard of VAX 780, but that VAX 11780, that was the standard of the time. So everybody compared their performance that we are 2 times the VAX. And so that system continues. Now I don't know what they use for the well-known system today, obviously, but the thing is, in those days, basically you took the time on your system and you took the time on the VAX, and they take the ratio. And the geometric mean of the ratios is reported as the SPEC int. SPEC int means integer performance on a SPEC benchmark. And so you will say this is SPEC int 3. 3 means it is 3 times more faster than, actually 3 times, so but higher is better here. So it is not execution time. Actually it is normalized, means if it takes, let's say, 3 seconds on the system and 1 second on VAX, then it will be 1/3. Performance will be 1/3. So it is, like that way. So speed is higher is better metric. A SPEC int. And so if you run many times, then you take actually you run many benchmarks or many applications, and you take the geometric mean of those to report as SPEC int. SPEC FP is a floating point. So you run floating point applications, and then you take the ratios, and then you present the number as SPEC FP. And then they also have something called SPEC rate. SPEC rate is basically the throughput. So you measure the jobs per second. Obviously, you take the ratio with the standard, and then you take the geometric mean of the ratio. This will give you the throughput ratio. So there are several things that I wanted you to notice about this. One is that they take geometric mean. So the question comes up, why geometric mean? You remember, does anybody remember what they do in the Microsoft workload? We had talked about Microsoft Windows. Yeah. They take the minimum. So the question is minimum better than the mean, right? Geometric mean. And so we can discuss that. And the second thing is they have three different things they are measuring. Integer, floating point, and rate. So one does not imply the other. If something has a better integer performance, does not mean that it has a better floating point performance or it has a better rate. Make sense? That one. Now geometric mean question, I will leave it alone right now because we are going to discuss that in detail when we go to the section, a whole chapter on mean. Oh, so basically you find the jobs per second on the standard system. And so make it higher is better always. I mean, see, both of these things are higher is better. SPEC int higher number is better. SPEC FP higher is better. SPEC rate higher is better. All right. So now you see some intricacies, whatever. I mean, some difficulties or some issues in designing a benchmark, right? So we go to more details of those. Basically, once you have a benchmark, then everybody is going to optimize their system to make sure that the performance on the benchmark is really good. And that includes compiler optimization. So they would basically use something that people will not normally use, even for optimization, but for this test, we got to be our best, right? So that's where it becomes basically non-representative of the real world. So SPEC came back and said, okay, all right, what we will do is we will let you do that, but you report that as a peak number. So when you say SPEC int of 5, that is your peak number, maximum number. But then you also run another benchmark, the same benchmark with a very standard minimal set of compiler parameters. So they specified 3 or 4 common ones that everybody uses. And so if you use those flags while compiling, then whatever number you get, that you report as baseline. So you report 2 numbers now. Baseline and peak. Baseline is with the minimum number of flags, minimum specified flags, and peak is whatever you want. Make sense? Okay, all right. But what happens is, while they require both, but who is going to present the peak baseline one? They might present it to whatever, but basically they only publicize the peak numbers and not the baseline numbers. Obviously, these are all marketing guys, and so you don't see much of the baseline numbers. And n CPU systems run n copies in parallel, but this is not representative because there is no queues of the waiting jobs. Suppose you have a 4 CPU system. In a normal environment, you might have hundreds of other processors running and there is a big queue for 4 CPUs. But here they will have 4 jobs running, exactly 4 CPUs being used, so there is no queue, there is no contention, which is not representative of the real world again. Make sense? So basically the goal of the benchmark is to be representative, and the goal of the people running the benchmark is to be the best. So they will create an environment, they will create everything so that they get the best number. Source code of commonly used programs are not available for use as benchmarks, so mostly open source. So the thing is, you cannot run, let's say, Microsoft Word or something, because that is source code is not available, right? But what you can run is the open source version of whatever, like Open Word or something. There is something. Open Office, yeah. So that you can run. So that's what you end up is most of the benchmarks are open sources. long run time allows jobs to run from cache. And nowadays the caches have become so big, so basically most of the jobs, these benchmarks, which are small programs generally, they just run from the cache. So there is no memory hierarchy, there is no paging, there is nothing going on there. Again, that is not representative. High performance and high price systems. So that was another thing, is that you get higher performance, but that is because you are buying $1 million system as compared to this $1,000 system. So they said, okay, why don't you put the ratio? I mean, people argued and then they agreed upon something called price performance ratio. But that's a very difficult thing to do, because what is the price of a system? If you go to a store and you ask what is the price, it depends. I mean, basically is whether this is on sale today or not. And second thing is how many you are buying. And there are many other factors that affect the price. Price is never fixed. So again, you have now two things that you can play with, not only the performance but also the price. Right? Price is easily manipulated and varied by the configurations. Algorithms and systems are developed to optimize benchmarks. And then what happens is, suppose you are developing an algorithm. You are a researcher, you are developing an algorithm. So you go to the benchmark, you say, well, we run the SPEC, whatever benchmark. There were lots of other benchmarks there. And then you tune it to make it the best for that benchmark. You change your parameters, tune it, right? And so again, if the benchmark is not representative, you can show that your performance is 2 times better than the rest of the world, but it may not be the real statement. I mean, it may not be a true statement. So benchmarking has lots of discussion going on, even still now, and these are some of the issues. So that brings us to the end of this chapter. And there were lots of benchmarks that we did not talk about, and I assume that you will read from the book. Okay, please do, because those will be in the quiz. Sorry, they will be in the exam. I just want to make sure that you read about those benchmarks. In particular, for example, MIPS we didn't talk about. It is very straightforward, millions of instructions per second. So there were originally benchmarks where you executed some number of instructions and you got the MIPS. Kernels, synthetic benchmarks. So these were originally the case, but now we are using industry standard benchmarks. SPEC. Benchmarks should be representative, portable, unbiased, scalable, measurable, repeatable, and explainable. So we talked about all these 6-7 properties for the benchmarks. And then we also learned that it is difficult to ensure representativeness of the benchmarks, because people can play with the compiler flags, they can play with the runtime configuration, and so on and so forth. Everything can be manipulated. And nowadays, price and energy consumption. Actually, I didn't talk about energy in before, but this is one of the things, is that in addition to the price, now people are thinking about how much in watts does it take, and what is the performance. For example, the recent system I have gotten, very simple, very cheap system, not very expensive, but it has a switch in it which says, and you plug it in, you say low energy, medium energy, or actually is auto energy, and then peak energy. With peak energy, I get peak performance. With low energy, I get low performance. With medium, whatever it wants. So what is the performance of that system? And so basically, you have to see how much energy it is consuming and then say the performance. Just like that price performance ratio, somebody has to come up with some kind of trade-off of energy versus performance. Okay, so energy has suddenly become very important nowadays, particularly in the data centers where you have thousands of CPUs running at the same time. And the homework is very simple. Basically, I want you to make a list of 25 benchmarks that are not discussed here. So don't go to SPEC, obviously, but there are so many other benchmarks, and you can just do a Google search. And basically the idea is that I need you to write just one sentence for each benchmark in your own words. So just don't take from Wikipedia, for example. If you go and you find the benchmarks, you'll find lots of them, but don't write their words. If we find that you're writing their words, then this is violation of the rules here. Okay? Just express it in your own words, and one sentence is all you have to write about each of them. Why I'm asking you to do this? So you get used to see what are the different kinds of benchmarks which are available. You don't need more than that right now. When you come back to your own algorithm or whatever you are trying to compare, then you will do a deeper search and read about the benchmarks for that particular one. And there are hundreds of these benchmarks, by the way.